Chapter 10, Rigid Body Dynamics, Part C, Principal Axes. In the previous lecture, we were introduced to the inertia tensor. The inertia tensor transforms an angular velocity vector into an angular momentum vector in the general case where the two are not necessarily parallel. The tensor is most conveniently expressed as a 3x3 matrix that transforms the components x, y, and z of the angular velocity vector into the different angular momentum components. Also in the previous lecture, we looked at the example of a point mass in the xy plane, and we calculated the inertia tensor if the x-coordinate was a and the y-coordinate was b. In this case, we simplify it so that both the x and the y coordinates of our point mass are the same. So we'll have a along each coordinate. In that case, the inertia tensor simplifies to this expression. We haven't talked about calculating the inertia tensor for a solid object yet, but we will. Here's looking ahead a little bit. Here's an example of a thin plate. So the idea is that this is like a thin object that doesn't have very much thickness in z, but it's like square in the xy plane. So it turns out that the inertia tensor for this object has a very similar form to our point mass. Notice that in both cases, since it doesn't have any extent in the z direction, these terms, these off-diagonal terms involving z are 0 in both cases. Notice also that the izz component is twice ixx and iyy. That's true for both of these cases. You can also notice that in this simple case of a point mass, the off-diagonal terms are just negative, the diagonal x and y terms. That's a little bit different for the case of the plate because of the distribution of mass in the xy plane. But these things have very similar forms, and so we're going to solve for the principal moments using the example of this thin plate. So let's define what a principal moment is. Every pivot point in every object has a set of 3 principal axes around which the object can spin without applying external torques. So remember that if you're spinning with no torque, that means that the angular momentum must be parallel to the angular velocity vector. So in other words, you can write that the angular momentum vector is just a scalar quantity, I sub k, times the angular velocity vector. This is the result from Physics 203. This is true around each principal axis of the object. The moments of inertia around those principal axes are called the principal moments. So these values right here, these ik values are the principal moments. There's one principal moment for each of the 3 principal axes. So we're letting k be an index that ranges from 1 to 3 for, say, the x, y, and z axes in that coordinate system. Okay, so let's let these unit vectors, omega 1, omega 2, and omega 3, point along the principal axes of our object. So we don't know what they are yet, but let's just define them to be aligned with the principal axes. So what we're looking for is when we apply the inertia tensor to one of these basis vectors, omega k, we get the same vector back with a scalar out in front of it, which we're going to define as lambda. So this I is going to be a 3x3 matrix, our inertia tensor. This omega k is going to be some vector, which is the same as the vector that we get back. And again, we get a scalar out in front of it. If you have an equation like this with a matrix, this is called an eigenvalue equation. You take a matrix, apply it to a vector, you basically just get the same vector out with some scaling out in front. So these omega k's are called the eigenvectors of the matrix I, and they define the three principal axes of rotation. So since our inertia tensor is a 3 by 3 matrix, we will have three eigenvalues associated with that matrix. Each eigenvector will have a corresponding eigenvalue. The eigenvalues are those lambda coefficients out in front, and they are the things that define, they will be equal to the moment of inertia around the corresponding principal axis. So again, we'll be trying to solve for three eigenvectors, and each eigenvector will have the corresponding eigenvalue. And what we want to do is solve this equation. So the way to do it, it requires just a little bit of matrix manipulation. So you probably already know about the identity matrix. The identity matrix is a matrix that has ones along the diagonal and 0 for the off-diagonal terms. So the identity matrix for a 3 by 3 matrix would have 3 ones along the diagonal and everything else 0. This is a bolded capital, it's a bolded 1. Don't get it confused with a capital I. The capital I is for the inertia tensor, the 1 is for the identity matrix. The property of the identity matrix is that for any vector u, you can multiply u by the identity matrix and you get the same vector back. Okay. So what this means is that when we have our eigenvalue equation up here, we can insert an identity matrix right before our vector omega, and it's not going to change the equation. So we can just insert a little one identity matrix right in there, and it's not affecting the equation at all. It's the same equation. The reason for inserting the identity matrix in here is that we can now let it multiply the eigenvalue in front of it, the lambda 1. So lambda times 1 is, you just take lambda, multiply it by the identity matrix, and you'll get a matrix with the lambdas along the diagonal and zeros everywhere else. All right, so let's keep that in mind, so that now what we're going to do is write the eigenvalue equation. We're just going to simply move this term from the right side over to the left side of the equation like this. And now that we have a matrix here, lambda 1, we can factor out the vector omega k, and the thing in parentheses are two matrices. We have our inertia tensor matrix, and then the lambda 1 is this matrix right up here. So we're looking for solutions to this equation. Our math friends tell us that it has non-zero solutions if and only if the determinant of this thing right here is equal to 0. So if you take the determinant of this thing and set it to equal to 0, that's a condition that there'll be non-zero solutions. Okay, so let's see what that looks like. Remember, I is our inertia tensor, so I'm writing it out in matrix form, showing all the components. Lambda times 1 is the identity matrix with the lambdas along the diagonal. So if we subtract these two matrices element by element, this is what we get. So we get the inertia tensor, and then just along the diagonal we're subtracting a lambda from that value. Here's the condition. This is a matrix form of our characteristic equation. This is the thing that has to be satisfied, that we need to solve in order to find the solutions. So to see how to do it, it's best to do it by way of an example. So let's take our example of the flat square plate, It's in the xy plane. It has very negligible thickness in the z direction. You'll just have to take my word for it for now that this is the inertia tensor. We've got numeric values inside the matrix, and you have it multiplied by the mass of the plate times the length of each side, a squared out in front. So we want to find the eigenvalues of I, which will be the principal moments of inertia. So because this matrix has an ma squared out in front, it's going to be easiest to define our eigenvalues as ma squared times lambda instead of just lambda. That way we can factor the ma squareds out. So this is just keeps it simple. We don't have to worry about the ma squared. You can just divide that into the 0. We want to take the determinant of this thing and solve for the lambda values. Once we find the lambda values, we can plug them back in here to find the moments of inertia. These lambda values will have to be multiplied by ma squared to get the actual rotational inertia. Okay, so we got to take this determinant of this 3 by 3 matrix. So remember that the way to do that is you break it up into 3 2 by 2 determinants. So what you do is you take the top left element here and write it out in front, so 1/3 minus lambda, and then you kind of cross out this term and this term, and then just take the determinant of this little 2 by 2 matrix. So you take the determinant of 1/3 minus lambda, 0, 0, 2/3 minus lambda. Then you move on to the next one. You look at this value. You cross out the row and the column that it belongs to, and then you write that it's equal to negative. You alternate the signs on these things. So the first one is a positive this term. Now you do a negative that term, then we're going to do a positive again. So you take negative 1/4, so you take a negative 1/4, and take the determinant of what's left over here. So we've got negative 1/4, 0, negative 1/4, 0, 0, and then 2/3 minus lambda, 0, 2/3 minus lambda. Okay, and then now we take that next one, which is 0. You cross out the row, cross out the column, and then you write 0 times the determinant of the matrix that's left over. So of course this is 0 times it, so this whole thing is going to go to 0. Okay, so if we simplify, if we just multiply out the determinant, this was the term out in front, this was the term out in front, and when you cross multiply the 2 by 2 determinant, so it looks like this, so it was, this is the 2 by 2 determinant we're solving for this first part right here. So you take this term, multiply it by that term, so you get 1/3 minus lambda times 2/3 minus lambda. So we're taking that times that, and then minus the off-diagonal terms, which is just 0. All right, and then we move on to evaluate the second determinant, which is equal to this. So we've got this big, long expression. We want to simplify it, so you can factor out this 2/3 minus lambda here and here. So you can factor that term out of both of these, bring it out in front. You get a 1/3 minus lambda squared minus a 1/16 from the 1/4 times the 1/4. This is now factored into kind of two factors. So the first one, if it is the thing that makes this equation 0, then lambda must equal 2/3. So the root of this equation, due to this part, would be lambda is 2/3. The second one is a quadratic term, and so we have to FOIL out that first term. You get this when you write it all out. And you can solve this equation using the quadratic equation. And so you get that lambda is either equal to 7/12 or 1/12. Just by, again, plugging in the quadratic equation, you get these results. Okay, so we have three roots. We've got lambda of 2/3, 7/12, or 1/12. So these lambdas let us calculate the principal moments. Remember that the principal moments were equal to ma squared times the lambda value. So when lambda equals 2/3, you plug it in here, you just get 2/3 ma squared. When lambda is 7/12, you get 7/12 ma squared. When lambda is 1/12, you get 1/12 ma squared. So we've found the principal moments, that's the moments of inertia around the principal axes. Now we have to figure out what those principal axes are. So the way we do it is we plug in one at a time each eigenvalue back into, which are the principal moments, back into the matrix equation and then solve for the principal axes. So let's look at the eigenvalue of lambda equals 2/3. We're going to label this lambda 1. The principal moment will be 2/3 ma squared. So remember that here's the determinant that we solved, right? We said that in order for this equation to have solutions, this determinant must equal 0. So when we set this determinant equal to 0, we solve for the eigenvalues, the lambda values. Now what we're going to do is take those lambda values and plug them into this equation here. So that's the that's the inertia tensor minus the lambdas along the diagonal multiplied by the vector, the omega vector equaling 0. So we're going to plug in the eigenvalues here and then use that to solve for omega. Okay, so here we are. This is our equation. That's the inertia tensor minus the lambdas times omega equals 0. We're going to plug in lambda equals 2/3 here, here, and here. So we're just plugging in 2/3 for the lambdas along the diagonal. Simplify that matrix and you get this. And remember, this kind of matrix multiplication is just shorthand for writing three equations. The first equation is like this top row multiplied by the vector equals 0, then the middle row multiply it by 0, and then the bottom row multiply it by 0. So let's look at the top row first. We'll have negative 1/3 times omega x, negative 1/3 times omega x, minus 1/4 omega y, minus 1/4 omega y, plus 0 times omega z. So I didn't include that one because it's just 0. The middle equation gives us negative 1/4 omega x, negative 1/4 omega x, plus negative 1/3 omega y, negative 1/3 omega y, and then a 0. And then the bottom one are just all zeros, so it doesn't really tell you anything. So we have two equations and two unknowns. When you solve this equation, if you took y and solved for y and plugged in the other one, you would actually find that omega x must equal omega y must equal 0 for both of these equations to be true. When you've got three equations here, so you might think that you could solve for omega x, omega y, and omega z, since you have three equations and three unknowns. Unfortunately, there's always a degeneracy present or a redundancy present in these equations. So from these three equations, you can only ever get two constraints at most. The third constraint comes from normalization. So if we want this to be a unit vector, omega x squared plus omega y squared plus omega z squared have to sum to 1. So that's our normalization constraint. If omega x and omega y are both equal to 0, then omega z must just equal to 1 or negative 1, but we choose the positive root. Okay, so this is our eigenvector for that first eigenvalue. So it turns out that this eigenvector is a axis that just points along the z-axis. Okay, so that that eigenvalue that we found corresponds to a rotation around the z-axis. Let's do the second eigenvalue. Second eigenvalue had lambda 2 is 7/12. Okay, so if you take the 7/12, plug it in for lambda, I've already done the math. This shows our equation with the lambda 2's already plugged in, just to save space. So I've already plugged it in along the diagonal. We're going to turn this into three equations like before. The top two equations, if you solve them simultaneously, you get omega y is negative omega x. This one tells us that omega z is 0. Okay, so here's our normalization equation. We know that omega z is 0. That goes away. If omega x is negative omega y, we can put a negative, well, this is the same as omega x squared plus omega x squared equals 1. So in other words, 2 omega x squared equals 1. In other words, omega x is the square root of 2 over 2. And omega y is just negative that. So we see that our eigenvector in this case is going to be square root of 2 over 2 x hat minus square root of 2 over 2 y hat. If you want to represent that in matrix form, you could write this square root of 2 over 2 with a 1 in the x component, negative 1 in the y component, 0 in the z component. So that's our second one. And now let's look at the third one. Lambda 3 is 1/12. I've already plugged in the 1/12 into the diagonal. Here's our equations. The first two tell us that omega y equals omega x. This one again tells us omega z is 0. Normalization. Same calculation as before. We now see that omega x equals omega y equals square root of 2 over 2. So this eigenvector points in both the positive x and positive y direction. So let's summarize what we found. We found that the first eigenvalue was 2/3 ma squared. That's the moment of inertia around this axis. So if our plate is here in the xy plane, the z-axis is coming out perpendicular to that plane. If you spin this square thin plate around the z-axis, you won't require torque, and this will be the moment of inertia around that axis. The second one we found had a moment of inertia of 7/12 ma squared. This eigenvector had a positive x component and a negative y component. So positive x, negative y, it'll be pointing down and to the right in the xy plane. So if we spin this plate around that vector, it will have a moment of inertia 7/12 ma squared, and again, you don't need a torque to do it. The third one is the one that goes diagonally through the square plate like this. It's got a moment of inertia of 1/12 ma squared. The eigenvector, or the principal axis, has equal x and equal y component, so it's a 45-degree angle and with a positive slope in the xy plane. So those are the only three axes that you can spin this object around that point and not require torque. Let's look at a simulation to see what it looks like. Here's the plate spinning around the z-axis. So you can see it's just spinning around like by one corner there. Here's the plate spinning around that diagonal with a negative slope. And here it is spinning around the third principal axis that cuts diagonally through the square. Okay, so that's basically it. Just one final thing to wrap up. So if you choose your axes, your x, y, and z axes, to be like they're stated in the problem originally, this is what the inertia tensor looks like, right? There's off-diagonal elements, and if you chose to spin it around the x or the y-axis, you'll see that the angular momentum does not line up with that rotation axis. If you rotate your coordinate frame so that now, say, your new x prime frame is in the maybe in the z direction, your y prime axis is in the direction of omega 2, and your z prime is in this direction, then in that coordinate frame, we diagonalize the inertia tensor. Okay. So in this case, if you spin it around your new transformed x, y, and z axes, then angular momentum vector will line up with the angular velocity vector. Also, something to remember is that the principal axes are tied to the object itself. Once this thing starts like spinning along some axis, then this matrix is going to start changing because this will be in a different orientation in your x, y, and z coordinates. However, if you transform into a coordinate system that's in the body frame, that is to say that is attached to the object itself, then this inertia tensor will always stay the same in this rotating reference frame. Okay, that's it. Hopefully this gives you enough examples to take on those first three homework problems calculating the principal moments.